thank thank the organizers for having me here, and also I'd like to acknowledge the hospitality of the Isaac Newton Institute. Some of the things I will try to show to you in these 20 minutes have been made while I was staying here in March, actually. Okay, so let's start. Let's start with photonic metamaterials. They are materials composed of building blocks, the properties of which we can control, and these building blocks are several times smaller than the wavelength of light. So with the design of these building blocks, we can then control the properties of, because we're talking about photonics metamaterials, so let's say the transmissivity of the light passing such materials, or polarization, or let's say the shape of the exiting light wave. Here's an example. So this is the first metamaterial that was done, with which, no, perhaps not the first, but the first one with which negative refraction was shown. So the scale here is 1 inch. So this is for microwaves. But since then, so negative refraction is refraction on the opposite side of the boundary normal, as we see here. So since then, we had seen many different structures made from many different materials, from metals, dielectric combinations of both, various geometries, and so on. But today, I'll talk about the split ring resonator particle shape. So that's the shape of interest in this talk. It's basically just a ring with a slit in the middle. It's interesting because it produces a magnetic dipole moment, so some sort of magnetic response. We get some sort of magnetic response from such a metamaterial, in contrast to normal material for which we know that the magnetic permeability is usually just equal to 1, more or less. Okay, how to connect the photonic metamaterials to the field of nematic fluids. Here are some papers we took some inspiration from. The top row is the more metamaterial row, and the bottom row is a bit like nanoparticles and nanoparticles in liquid crystals. So this paper talks about actual building blocks for metamaterials mimicking the shape of liquid crystals. Then there's this variety of work that's been done on just metamaterial particles being covered with liquid crystals, and then their properties being tuned with the properties of liquid crystals, so with the temperature, or with external fields, sorry. So here we have, for instance, golden nanorods being assembled in liquid crystal defects, and the properties of this material also then being tuned, so the transmissivity also being tuned with the properties of the liquid crystal itself. This last picture here is just a representative for variety of papers, again, being done on the assembly of particles in liquid crystals, so all sorts of interactions going on between differently shaped particles. Okay. So the first part of my talk, at least, will focus on this split ring resonator shape, a bit more abstract than this, perhaps, being put into liquid crystals, and then let's see what happens. So we want to facilitate the formation of some stable colloidal crystals, but the main focus is for photonic applications then. So the outline of this talk, firstly, I'll just briefly go through the methods, then what I've been talking up until now. So the choice of specific geometrical parameters for the split ring over here, and then the photonic properties of such materials. Then I'll skip to something a bit different, so to a homogeneous metamaterial, and how, so homogeneous metamaterial with different signs of the eigen values of the permittivity tensor, so perpendicular and extraordinary and ordinary permittivity, just to show how light could be controlled very well with such materials. And then we'll go to conclusions. Briefly about the methods. So all the simulations of the nematic liquid crystal fields have been done with Landau-Desgen free energy minimization methods, which I guess most of the audience is relatively familiar of. The photonic simulations, however, have been done with finite difference time domain method, which is basically just if I say this in the most basic form, it's just numerical integration of Maxwell's equations, so we get a complete time and space information about all of the fields. However, because this is very time-consuming and also memory-consuming, there are some tricks that can be done. So FDTD uses this generalized E lattice, which is basically just cubic lattice, or let's say 2 cubic lattices, one for electric and one for magnetic field, being stacked next to each other. So this reduces the number of memory points we have to keep. So basically, how does this look like? We have a calculation cell, we have a wave source coming from outside of the calculation cell, and then we have the absorbing boundary around it with which we simulate the effect of free space. So we pretend we are sending light into infinity. How do we simulate different materials inside of the cell? By pointing different values of the permittivity. So for the liquid crystal, we have to have tensorial permittivity, and for the metallic particles, because we will be simulating the golden split rings, we have to introduce some sort of absorption and frequency-dependent permittivity function. Okay, so let's start with the geometrical design. So how have we decided on the specific geometry of the split ring? So here we have this split ring, and we can vary various various of its parameters. So let's say the width of the arms here, the width of the slit, the height of the particle, and so on. So what we want to keep from this particle is we want to have it square with a hole in the middle and a slit over here. So this is just a very abstract split ring resonator, and we want to keep this because of the photonics, as I've spoken before. Still, this is quite a complicated particle. It would form many metastable clusters, so it would be difficult to get a stable structure. So our idea was to use specifically optimized particle to get a symmetrical, so for one particle to get a symmetrical orientation in the nematic field, so to raise the probability for it to form stable colloidal clusters. So here are some examples of the calculations. Basically, phi angle here is the angle between the far field anchoring of the nematic and the particle itself. So then we just analyzed the angle between the far field director and the particle, and we can see that this free energy changes a lot by changing the material parameters of the particle. But we'll skip the details here. So from this analysis here, we've decided on 2 types of particles that are most promising. So we can see that both of them are symmetric with regards to the nematic field, type 1, type 2, and then we analyzed them a bit further. But in the end, we decided for this type 1 particle because we also analyzed some pair interaction potentials. And for this thicker particle here, it turns out that the interaction between 2 particles stacking on top of each other is repulsive. Yeah, and so then we analyzed the 2D and 3D colloidal crystals. Yeah, and we figured out, so we analyzed the displacement between the particles. So what we did was take a particle, put it into a cell with periodic boundary condition, and then varied the size of the cell. So effectively, we varied the displacement between the separate particles. And we see that the minimum of the free energy is at the smallest tested displacement. So this is for 2D crystals, for 3D crystals, so X and Y displacement, so in this plane, and for the Z displacement as well. So our simulations show us that this type of particle, so shown here, with specific geometric parameters we have shown, so that these 2 configurations would be stable. Okay. Now let's switch to photonic properties. How does this behave when we shine light upon it? So we take one particle, put it into a cell we have the nematic liquid crystal profile we have calculated before around it, and then we put on a plane wave. For various wavelengths, for a wide range of wavelengths, and also for the two orthogonal polarizations, so one along X and one along Y, so this one crosses the slit. And we look at the transmissivity. So we look at how much energy we can get at the top of the calculating cell. So what this tells us is how much energy the particle has basically eaten up in the middle. And then we look at these curves here, the transmissivity curves, and we see some maxima and minima. So we can look at the field profiles of these maxima and minima here. And we see that some sort of resonance is going on, but let's think about how we can understand this further. So we can look to this through the prism of this LC circuit explanation. LC here doesn't stand for a liquid crystal, but for capacitor and coil, so inductance and capacitance. So basically what we do, we assign to the parts of the split ring, we assign coil and capacitors, coils and capacitors. And then we say, okay, so this is effectively a circuit, and we drive it with an external electric field, so electromagnetic field in our case, but electric field. And then because we have an LC circuit, we can calculate what the resonant frequency is. And we compare that with our simulations, and we see that the numbers don't match up exactly, but at least for an order of magnitude, I mean, it's better than an order of magnitude, perhaps like 30%. So it matches up. And also, you can almost see the profiles of the capacitors and the antennas and so on. Okay. Then we extended this to 2D and 3D materials as well. Here are some pictures for the 3D only. So this is so we took periodic boundary conditions for. So we took one particle, put periodic boundary conditions in the horizontal directions. So we got effectively a 2D crystal, and then we took 10 layers of that, and that's our 3D crystal here. So here's the electric field inside of the crystal, squared actually, and also normalized. For various different wavelengths, what we see is, so basically exponential decay because of the absorption inside of the golden particles. Yeah, well, what happens for 2D and 3D materials, such materials, is so two things because of the, so we still do get resonant behavior. However, because of the higher density of absorptive gold we have in our system, we get much higher levels of absorption. So for instance, here, around here, we only get maximum of 20%. Yeah, and also these resonances do move a little because of the coupling between the individual particles. So also another interesting thing we wanted to show with these materials was the possibility of tuning of this material with the properties of the liquid crystal. So this is again a curve for the one particle from I showed before. But for 3 different values of the extraordinary refractive index, and okay, perhaps it's not really that visible that well, but this resonance does move, and it looks really not a lot on this graph, but when you plot it, it's for about, let's say, 500 nanometers. So if you change the properties of the liquid crystal. Yeah. Okay, so with this, I'd like to conclude this 2D, 3D metamaterials story. And go to something completely different, as I've said. So I'd like to finish with the control of the flow of light with birefringent metamaterials. So I'll talk about hyperbolic sorry, 5 minutes, 4 minutes, okay, I'll be quick. So again, I'll take this permittivity tensor, and ordinary value and extraordinary value will have different sign. You could do similar thing with the permeability tensor, but I'll just focus on this one because, yeah. So we have vacuum on the bottom, this strange material on top. We can change the optical axis of this material. Then we shine light on it and wonder what happens. So how does this beam refract? So when we quickly notice that many different possibilities are possible. So for instance, here we have some parameters and some optical axis that gives us, so what we send in is positive, so we have a positive wave vector. But then on the other side, we have a negative wave vector. So wave vector is orthogonal. This is, again, electric field. So this is orthogonal to the phase, yeah. So, and the Poynting vector, however, is positive. But then for some other combination of parameters, again, optic axis, some other parameters, we can get negative Poynting vector refraction and positive wave vector refraction. So we could talk about some generalization of the Snell law for the refraction of light into these special materials. So what we notice is, so we can get for the same parameters, so this is now for the same parameters, but just for different optical axes. For this optical axis, we get all positive refraction, and then here we get this mixed refraction, so positive wave vector, negative Poynting vector, and then for some combinations we get, okay, absorption is not the right thing to say. We get no propagating solutions for the wave vector. Let's take just a quick step back. So now we're sending light perpendicularly to the surface. And just by changing, so the parameters are again the same as here. Just by changing the optical axis, we can now switch the direction of the Poynting vector from going to the left, a bit less to the left, up, and then to the right completely. So how come this changes? So this can change so much with just the optical axis variation. Well, it follows from the dispersion relation, because we have some eigenvalues negative, changes from the ellipsoid, as we know, to a hyperboloid. So for some angles, we don't get any propagating solutions. So for angles here in between, so this is these angles, and then for some angles, we get solutions. Okay, this is just the last slide. Really. So of course the next natural thought for a liquid crystal researcher is, so what if we twist this optical axis into some different profiles? So for instance, if we take this -1 defect, we see that for light propagating straight in, it will deflect, so it won't want, so perhaps I should behave, yeah. So it deflects from the center of the defect. So, but for some other profile we choose, then again we send light in. We see that the light wants to go to the center of the defect, but then doesn't want to propagate any further. Yeah, I'll just leave it at that. Here are some conclusions. So we optimize the geometrical parameters. We analyze the optical transmittivities. So that was about the 2D, 3D colloidal crystals. And then we simulated some combinations of positive, negative birefringent material. And we saw that we could control light very well with it. That will be all. Thank you. Yes?
On the 2D, 3D structures, what is the dependence on the K vector, not just the wavelength? The option or transmissivity?
Where? Sorry.
In the constructs you made from the split ring resonance,
yes,
it's only incident perpendicular to the
yes, because we're sending in plane waves. So yeah, the wave vector is always perpendicular to the structure. Yes, I should have made that clear. Yeah, we just changed the polarization. So the E vector can point either in this direction or in this direction.
You could do more. Just this
yeah, sure.
Okay, we should